Okay, welcome back. So, in the last video, I finished talking about the physics practicals on waves, and thereby I finished the physics practicals on mechanics and waves. So, in this video and from this video onwards, I'll be talking about some physics practicals on heat, physics heat. So, to begin with the physics practicals, I will do a simple practical in which I will find the specific heat capacity of a given solid. So, to introduce with, I need to explain to you as to what is meant by the specific heat capacity of a solid. Now you may already know by now, but let me introduce as it is necessary to explain about the concepts of this video. So the specific heat capacity of a solid is the amount of heat needed to raise the temperature of a unit mass by 1 degree of Celsius. So if the mass of the object whose specific heat capacity is calculated is m, the specific heat capacity is C, and the heat needed to raise the temperature of the system by theta Celsius or theta degrees Kelvin theta degrees of Celsius or theta Kelvin is Q. You can say that Q is equal to mc theta. So this is a very popular equation. You may already know by now, some of you, and some of you may not know by now, but I need to introduce so because actually this equation is greatly used in this video when introducing about the concepts of the specific heat capacity. So Q equals mc theta. So let's do a simple experiment to find the C value of C for a given solid. So the setup that I'll be using here is like this. Now this is actually a small tube in which I introduce hot or actually warm objects. Now actually what I mean by warm objects is that now this is a calorimeter, you can see that, and this is an external beaker. So external beaker is used so that this calorimeter doesn't touch the table or the any other surface that we are doing this experiment. So there's no actually there's actually a minimum heat loss by conduction, so you can easily use wood or some heat insulator here. So there's no heat conduction, and what you do here is that you have a thermometer here, you have a stirrer to stir this water. So water and the calorimeter is initially at the same temperature. So what I mean by warm objects is that the temperature, initial temperature of these objects is greater than the initial temperature of the water, water and the calorimeter system. So what I'll do is that I'll do a simple experiment like this. I'll take the mass of the calorimeter and the stirrer to be m1, the mass of the calorimeter, the stirrer and the water to be m2, the initial temperature of the calorimeter. So initial temperature of the calorimeter means the initial temperature of the stirrer as well as the initial temperature of the water, because we think that the initial system is composed of the calorimeter, stirrer and water. So that is equal to theta 1. So total mass of the objects I'll take as m3, initial temperature of the objects as theta 2, and the final temperature of the system is theta. Now you know by the concept of thermal equilibrium that when some hot object or a warm object is introduced to a cold system, what actually happens is that the hot or the warm object will cool down and the cool system will warm up, so that finally both these temperatures come to a thermal equilibrium and a temperature equilibrium. So they will attain the same temperature. So the final temperature of the system means when the objects are completely inside the water, so the temperature of the objects, the temperature of the water, temperature of the calorimeter and the temperature of the stirrer, everything would be theta. Alright. Furthermore, I'll take the specific heat capacity of the calorimeter to be C, the specific heat capacity of water to be Cw, and specific heat capacity of the objects to be C naught. So assuming that the heat loss to the environment is negligible, you can say from the theories of calorimetry, you can say that the heat gain by one object or a system of objects is equal to the heat loss by one object or the system of objects. So modifying that statement, I can say heat emitted by the objects is equal to heat gained by water plus calorimeter. Now you know that at first or initially the objects are at a higher temperature. So what actually happens is that these objects emit heat to the water plus the calorimeter system, and the water and the calorimeter system gain heat. So there is actually a thermal equilibrium after some time. So you can write a sample statement for this as you take in the definitions or the values you took in the last slide. These values, you can say the heat the heat emitted by the objects is equal to the mass of the objects, which is m3, times the specific heat capacity of the objects times the temperature difference. So the initial temperature of the objects I took as theta2 and the final temperature is theta. So the temperature difference is theta2 minus theta. So this heat is emitted to the water and the calorimeter system, and the calorimeter will gain heat as well as the water. So since the mass and the specific heat capacities of the calorimeter and water are different, we have to write these statements separately. However, water and the calorimeter are initially at the same temperature, so you can factorize out the final temperature of the water plus the calorimeter system. So you know that the water and the calorimeter were at an initial temperature of theta1, and they will gain heat to a temperature of theta. So you can say that the temperature difference for the water and the calorimeter system is theta minus theta1. You have to multiply that by the calorimeter. When you think about the calorimeter, the mass of the calorimeter we took as m1, so ignore the mass of the stirrer, right? Ignore the stirrer is a very light object. So mass of the calorimeter is m1 times its specific heat capacity is C plus mass of water. So mass of water, so you know, when you subtract this equation from this equation, mass of calorimeter will cancel off, the mass of the stirrer will cancel off, so water will be remaining here. So water is equal to m2 minus m1, so the mass of water is m2 minus m1 times its specific heat capacity Cw. So this is the statement you can write. So actually you have been given the mass, so you can find the mass of m1, you can find the mass of m2, so you can find the mass of m2 minus m1, you can find the mass of m3. Also you can find the values of theta2, theta1 and theta. However, you don't know the value of C0, so C0 is the value that you can find here. So you can isolate C0 like this by dividing both sides by m3 times theta2 minus theta. So by this relationship we can find the specific heat capacity of the objects. So if we can do a sample experiment like this. So the method of this experiment is that first of all we measure the weight of the calorimeter and the stirrer, so that is actually m1. So as a second step we need to find the mass of water. So what we do is we pour water to the calorimeter, so that water fills about 1/3 of the calorimeter's volume. So actually this 1/3 is actually, we don't need actually 1/3, it can be 1/4 or even 1/5 or even 3/10, right? But it shouldn't be at least half. It should be actually less than half, because you know that the mass of these objects you can say that you have to add at least considering about the volume of the objects. If the volume of the object is very small, if you put some coins or something, you can say that you have to put numerous coins. So the number of coins is a large value. So when you add coins or any other metal or any other thing that will pass off heat to the water and the calorimeter system, what actually happens is that the level of water will rise. So you have to consider that, and initially you have to limit at least to half, right? So it's better if you limit to half, or even 1/3 is the most precise value, right? So I have taken 1/3 here. So as the third step, what you do is you measure the total weight of the objects to be about thrice of the weight of the total volume of water. So that's the reason as to why. Now this is actually a mandatory step, right? So that is the actual reason as to why I explained in step 2 that pour water to the calorimeter, so that water fills about 1/3 of the calorimeter's volume. Now since the total weight of the objects is thrice the weight of the total volume of water, the total volume of water that will be happening is the weight of the water plus thrice the weight of the water, so that will be 4 times the total volume of water, weight of the total volume of water. So the calorimeter should be sufficient, the volume of the calorimeter should be sufficient to hold all this mass, actually to hold all this volume, so that water doesn't spill off or water doesn't flow off. So you have to consider that. So that's important. So as the fourth step, you can use various heaters, but the best heater you can use is the Nicholson heater. So I will introduce about the concept of Nicholson heater in one of the next slides in the next few minutes. So don't thoroughly think about that. I will explain about the Nicholson heater. So there are also many other means through which you can heat these objects, but the best option is the Nicholson heater. And then you have to record the initial temperature. So the initial temperature of the objects we took as theta2. Then at the fifth step, what you have to do is we have to find the mass of the final system and the final temperature. So to do that, we introduce the objects to the calorimeter plus water system and stir the objects so that the heat is thoroughly and equally distributed along the water column. So what actually happens is that after some time, the temperature of the objects will decrease to a temperature of theta as we took, and the temperature of the water and the calorimeter system will increase from theta 1 to a temperature of theta. So there will be a thermal equilibrium as well as a temperature equilibrium. So we can record the final temperature of the system to be theta. So that's it about the method of finding the specific heat capacity of a given solid. So let's consider about some important points in this experiment. Now, as I mentioned here in this slide, now these two supports are needed to prevent conduction. There are three main ways. There are three main ways as to how heat can be lost. Right? Three main ways. One method is through conduction. Conduction means passing the heat from one electron to another electron or from one atom to another atom. The other method is convection through convection currents of air. Right? It can be natural convection or artificial forced convection. And the final method is through radiation. So to prevent now in this assumption here you said we assume that assuming that the heat loss to the environment as negligible. Assuming that the heat loss to the environment as negligible, if you make an assumption like that, you need to make sure that your assumption is working correctly. So what you do here is that to make sure that your assumption is correct and you are working correctly, accurately, what you do is the transfer of heat to the environment during the process difficulties for the successful completion. So what you can do is to minimize them. So as I mentioned, there are three methods as to how heat can be lost from a system. One is conduction, the second is convection, and the final is radiation. So to prevent heat loss from conduction, what you can do is that you can cover the calorimeter with heat insulators. For example, now in the case that I explained in a few slides back, in fact, now these are heat insulators. You can easily make these supports out of wood or any other heat insulator or rubber or any other, so that these supports can hold the whole final system mass of m3g, where the mass is m3 and the mass of m3 plus m2 plus m1 times g. And also there's another method of covering by heat insulators is that we can cover the whole setup. For example, you can take this external beaker like this. You can put the calorimeter. So before introducing water and the objects, you can introduce some rubber like this, rubber or sand or something like that, any heat insulator here, and then put the water, take the initial temperature, then actually record the final temperature, initial temperature of objects, and then introduce the objects and then measure the final temperature. So those are two ways of insulating to prevent conduction. So to prevent convection, what you do is that you can close the calorimeter with an insulating lid, right? So in this case, you can put a lid here, right? So convection currents need air to flow, right? Convection currents, either natural or forced convection. So convection does not occur here, right? Doesn't occur because there's no forced air flow over this calorimeter and the water column like this. There's no air flow because although there's air flow, that will not affect because the lid closes this system. So that is a method to prevent convection. So to minimize radiation, what you can do is that you can polish the surface. Your radiation is somewhat of a complex topic, so I will put a video on radiation in the future. So you will learn in radiation that when you polish a surface, the radiation can be minimized. So that's about a concept on radiation. So just remember that you can prevent radiation, or you can minimize the heat loss from radiation by polishing or by making a surface lustrous, right? So for the quick transmission, as the second important step, for the quick transmission of heat from the objects to water, small pieces of objects should be used instead of large pieces. Now, when using large pieces, what actually happens is that if you take a large piece, the temperature of the outer surface of the objects may not be equal to the temperature of the inner surface, because there's actually a temperature distribution. There's a large distance over which the temperature can distribute. So the temperature difference may not be zero. The internal temperature may be some, say, 15 degrees of Celsius, and the outside temperature may be, say, 16 or 17, right? Even points of Celsius increase or decrease. So what actually happens is that these objects, so we can say that there's an error when calculating, but what actually happens is that these objects take a lot of time to provide heat to water. So that's actually an error. We consider that to be an error. So also, when you are using extremely small pieces like dust or in powder form, it is also not easy to do this experiment because they will absorb water. So the best process to do this is to use medium size pieces, right? So that's an important step. And another important step is about the Nicholson heater. So I'll explain about the Nicholson heater. So the Nicholson heater is an instrument like this. You have a small jar like thing. You have an inlet here, another inlet here. So what actually happens is that you first of all you introduce the object to the heater like this. You can put objects here, and so they will get deposited here. Because of the case that can be lifted to free objects here, because of this case, the objects will not fall or would not travel to the calorimeter unless this case is lifted. So what we do as the second step is that we introduce water here. And now the Nicholson heater is filled both with water and the objects. So we provide heat, right, through a heater, Bunsen burner or any other heater. We provide heat to this system so that the water boils. Now you know that this surface through which the objects and the water is separated is made out of a heat conductor. So when water is heated to some temperature, say 70 degrees of Celsius, what happens is that now this heat is transferred to this intersurface and through this intersurface to these objects. So when water heats, simultaneously the temperature of the objects will also increase. So you can put a thermometer here. So when you introduce a thermometer, you can measure the temperature of the system. When the temperature of the system is measured to some value, so you can take any temperature, but the temperature, so we should not let the temperature go past 100 degrees Celsius, because when we introduce these objects to water, what actually happens is that when the temperature is greater than 100 degrees Celsius, some water may evaporate, because 100 degrees of Celsius is the boiling point, or 373 Kelvin or 212 Fahrenheit is actually the boiling point of water. So we should heat the objects to a temperature less than 100 degrees Celsius. So it's better always to be a precise value of 70 to 80 degrees of Celsius. So as the final step, what we do is we keep the apparatus like that. So this tube here is the outlet from the Nicholson heater that you see here, this tube like thing. So what you do is that you now open this lid or lift this lid so that the objects are free to move to the calorimeter. So as I mentioned, as I showed you in one of the previous slides, along this tube it will go to the calorimeter, and it should be in a very slow motion. So it's better if you can slant this much more, but in the case of a Nicholson heater, this is actually produced with some inclination, but you can change that. So you can do the practical like that. So it's all about finding the specific heat capacity of a solid. So in this video I explained to you about as to what the specific heat capacity of a solid is, how we can find the specific heat capacity of a solid by a simple experiment, and what factors we need to keep in mind, and what are the important points of that experiment. So this video is actually the beginning of the video series of videos on here physics practicals. So in the next video I'll be explaining you with some more physics practicals in convection, conduction, and the other concepts on heat. So I'll proceed along the topics of physics from the next video, and thanks for watching this video, and see you then.